Hello there, welcome to another presentation. This time we're going to look at the scientific method in general, the hypothesis, postulates, theories and laws, and then we're going to look at Newton's second law in particular. So let's start off. What is a scientific method? First of all, number one, define a question. Number two, make observations. Number three, form a hypothesis. Number four, experiment to test your hypothesis. Number five, analyze and interpret data. Number six, draw conclusions. Do the observations support your hypothesis? If no, try again. Make a new one. If yes, communicate your findings. This is courtesy of the Open University, a great little flowchart. Let's look at these terms. The scientific method. So the hypothesis, for example, how does the length of string affect the motion of a pendulum? A postulate, for example, is a little bit more advanced. You've got here Einstein's two postulates for special relativity. And he postulated, or had an idea, that speed of light is constant and that the laws of physics apply to all inertial frames. Then you have a theory which is stronger than a postulate. So you have, for example, quantum theory and Big Bang theory. And then you have a law, for example, thermodynamics, energy, momentum, and these have to be true under all circumstances. So these are physical laws which measure the result of something happening. The example now move on to Newton's second law. Courtesy of Wikipedia, the change of motion of an object is proportional to the force impressed and is made in the direction of a straight line in which the force is impressed. In mathematical terms, you have F, which is the force here with a vector notation, and the P is momentum, and momentum is a vector, P, and then you have d by dt, so it's the rate of change of momentum. Next page, force is rate of change of momentum. Now momentum is mass times velocity. Using the chain rule, d by dx of uv, where you have these two aspects that are both differentiable, you assume one is constant and you multiply by the differential of the first one, u dv by dx, and then you assume the second one is constant and you multiply that by the differential of the first. So d by dx of uv, the product here, the product rule, is u dv by dx plus v du by dx. So apply that to F equals dp by dt, because P is mv. Put it in there, take out the m first, m dv by dt plus v dm by dt. There's a d miss in there. And then you end up with d by dt equals m dv by dt is ma. But v dm by dt, what does that mean? So you have m times the rate of change of velocity, which is acceleration, but the velocity times the rate of change of mass. How can the mass change with time? And we're noting here that c, the speed of light, is 3 times 10 to the 8 meters per second. So next stage, you get another courtesy of the Open University, where we have a speed of light c in multiples up to c of a quarter of c, a half of c, and 3/4 of c. The Newtonian law, P equals mv, is a straight line as you approach mc, 2mc, 3mc momentum. However, this is relativity, where you have, eventually you have this kind of asymptote curve here to that line where you cannot reach the speed of light. It's impossible. So rewriting that one just a little bit simpler, P equals mv, again with vector notation, 1 minus v squared upon c squared, F equals dp by dt, which is ma plus what? So when v, that v here is 0, you have 1 minus 0 squared over c squared, which of course is 1 minus 0, square root of 1 is 1, so p equals mv. Happy days for that period. You've got a nice compliance with that law. However, when v equals c, this part here, so you have 1 minus c squared upon c squared, which is 1 minus 1, which is the square root of 0, and of course you can't do that, it's undefined. That's why you get this asymptotic carries on for infinity. So the law is a law which must be true at all times under all circumstances, breaks down as you approach the speed of light. So even laws are not always true under all circumstances. Then we equate, if we look at Newton's second law and the equation of gravity, F equals ma, F grav equals g, product of m1 m2 over r squared in the r hat direction, make them equal, ma equals g m1 m2 over r squared in the r hat direction, and acceleration due to gravity is g m over r squared in the r hat, and then you've got this quotation of the gravitational constant, which is an incredibly small number. It's almost impossible to measure. That's the precision to which it's been measured, 6.673 plus or minus 0.0015 times 10 to the minus 11. So it goes 0.000000000, incredibly small number of Newton meter squared per kilogram squared. So which question applies to you then? This is completely off spec here. Would you believe in God and be willing to consider submitting your life to him if you saw compelling scientific evidence for his existence? If this evidence was shown to be increasing as we learn more about the universe and the record of nature. This is what we know and what we can know. Or would you not believe in God until the scientific evidence eliminates all other conceivable alternative explanations for the universe and its life? So what we know and can know, and this is what we have, is unknown and unknowable. And here are the references. So a very quick video looking at laws, theories, postulates, the whole lot, just to get a scientific method and just to show that even with a law, it doesn't always mean that it's actually true at all times. So a healthy dash of skepticism when it comes to even a scientific method. Thank you for watching, and please like and subscribe, and any comments please. Thank you.